Okay, in this video, we are going to work out delta H for this reaction, and this is revision from year 12 stuff. Well, what we have got ethene, and they're going to react with hydrogen to form ethane. So it's an addition reaction. Just so I've written it down as the molecular formula there. All right. And what have they given us data-wise? They've given us delta HF. Okay, so when we do that, normally we draw a Hess's law cycle. So I say this is all should be revision, and then I'm going to show you how to do it a slightly different way. But let's do the old way. We would have we write the equation up here, and in Hess's law cycle we usually have three things, don't we? And we always think, what is the third thing to put down here? What we're going to put down here, right? Well, we're given delta HF data. So when you're given delta HF data, you should put the elements and the standard states down here. So the elements and standard states are going to be 2 carbons, solid, and 2 carbons, solid, and 3 hydrogens, gases. Okay, delta HF, which way do the arrows go? Well, we're forming these compounds, so the arrows have got to go up, haven't they? And we want to find out this value, delta H, for that bit of the cycle there. All right, let's look at this arrow here. What we're doing there, we're forming 1 mole of ethene. The delta HF of ethene is plus 52, so that's going to be plus 52 kilojoules on there. And on this one, on this arrow, we're forming 1 mole of ethane. Delta H value for that one is minus 85, so that's going to be minus 85 kilojoules on that. Okay, now the normal thing we do is say we want to go, well, I want to go from here to here, don't I? So what am I going to do? I'm going to go down that way, and I'm going against the arrow there, so that becomes, we change the sign, and we're going up there with the arrow, so you keep the sign. And you write down delta H for the reaction then. Well, it's going to be plus 52. We change that to minus because we're going against the sign. Minus 52. And this one, minus 85. Add those together. We get minus 137 kilojoules. So that is the answer to that problem there. 137 kilojoules, and it's exothermic. Okay, so that's the way we've done it at we did it in year 12, and we carry on doing that way at all. That's perfectly fine. But there is a slightly different way you can show, and on you do it on an energy diagram. Okay, so I rub this out and show you this. This is going to help us when working out lattice enthalpy. That's why I've showed you a different way of doing that. So what we've got here on this axis, we're going to have energy, right, going up. And really, what kind of energy here we've got was going to be chemical energy, okay? So the further, when we're going up, chemical energy is increasing. And obviously that is because thermal energy is being converted into chemical energy. So when we're going up, that is going to be an endothermic, that's the endothermic direction. And obviously when we're going down, we're converting chemical energy into heat energy, so that's going to be exothermic, any change where you go down. Yeah. Okay, so let's start off with the elements in the standard states. And so we're going to have carbon, 2 carbon, solid, and 3H2 gas. And I'm going to say that is their enthalpy, all right, or their energy internal. That's good. That's where they are. Okay, I should say enthalpy rather than energy, shouldn't I? Really? Okay. Right. Now, let's think about turning it all into that stuff, into ethene. Okay. Now that's when we turn the elements in the standard states into ethene, that's this one here. It's exothermic, isn't it? It's minus 85 kilojoules. That's delta HF for ethene. So exothermic is going down. So I should draw my ethane down here. Sorry. So I've got C2H6. And how much energy is that going to draw here? It is, right, the arrow is going down, and it is going to be minus 85. And I don't really need to put the minus on there because we can see it's exotherm. We know it's minus because the arrow is going down. Now let's think about what happens when we, for this, okay? When we're forming ethene from its elements in the standard states, that's endothermic. It's positive, this value here. It's plus 52. So that means the arrow here is going to have to go up. So I'm going to draw it roughly to scale. So I'm going to put ethene here, C2H4 gas. And what's happened to the other hydrogen? Well, nothing. So we just write that down as H2. We haven't done anything to that. And here, it's endothermic, so the arrow is going up. So what value am I going to put on that? It's plus 52. Right, so what are we interested in? Which change? Well, we want to know the change going from here, ethene plus hydrogen going down to ethane. Well, you can see from this diagram, all you've got to do is add those two numbers together, haven't you? Which is 137, and I haven't worried about the signs there. I'm just looking at it visually. I can see that, I've clearly got to add those two things together. It's just like looking at the heights of things, heights of buildings or something, And then I decide, right, is that a positive or a negative value there? Well, the arrow is moving down. That's the endothermic direction. So that's that. So it's 137 kilojoules. So that's delta H for that reaction. So that's just showing you how to do, instead of drawing it out like as a triangle, just drawing it as this energy diagram here. Right, give you one more example of that. Okay, so before we finish, so we're going to have, let's say, this reaction. We want to find delta H for this reaction. Carbon solid plus 2H2 gas going to form methane gas. Now that is actually that reaction there. What we're doing, we're forming 1 mole of methane from its elements in the standard states. That is actually delta HF. That's what this value is here. It's delta HF, isn't it? And the data they give us, well, they give us delta H combustion data. So they give us methane for carbon and for H2. Delta HC here. Delta H combustion standard, right, in kilojoules per mole. For methane, it's minus 890 kilojoules. For carbon, it's minus 393. And for hydrogen, it's minus 286. Let's do this as, well, how would we normally do this then? Well, we'd write down, there's our, just turn that into a chart. Now, I'm not sure if I can move that as one object or not. No, it won't let me do it, okay. So, right, so how do we do this? Normally we'd say, we'd say carbon plus 2 hydrogens goes to CH4. They're giving us delta H combustion data. So down here we want our combustion products, which is carbon dioxide and 2H2O. Which way do we draw our arrows? Well, we are burning this stuff, aren't we? So that arrow goes down, and we're burning the methane. That arrow goes down. If you want to balance it, you could put in. You're going to need 2 oxygens here. Okay, 2O2. And 2O2 there. We can forget about those oxygens really though. And what we're doing, well, on this arrow here, we are burning 1 mole of carbon, so that's minus 393, and 2 moles of hydrogen, so that's going to be 2 times 286, yeah, 286 for height, and that one for, yeah. So add all that up together on a calculator, and we get 965, that's minus 965 kilojoules. This arrow is more straightforward, isn't it? All we're doing is we're burning 1 mole of methane, so that's going to be minus 890 on that arrow. Okay, so what's delta H, which is delta H for this reaction that we're interested in, which is actually delta HF for methane, isn't it? As well, what we're doing on this arrow, well, we're going with the arrow, so that's minus 965, and then we've got to go against the arrow here. So what we do to that, that turn that into plus, change the sign, plus 890, and that is equal to minus 75 kilojoules per mole. Okay, so that's how we would have done it. If you do it as one of these diagrams, so we have going to put energy down here. Right, now let's think what we're going to have. Right, I'm going to put our carbon and hydrogen here. So carbon, solid, and 2 hydrogen, gas. Okay, and we are going to burn them into carbon dioxide and water, which is exothermic. So my carbon dioxide and water is going to be down here, CO2 and 2H2O. And that is going to be like that. Now we are burning, so that is going to be burning 1 carbon, so that's minus 393, and 2 hydrogens, so that's 2 times minus 286. We worked out before, that is equal to minus 965 kilojoules per mole. So we're going to get rid of, well, kilojoules anyway. Let's get rid of that. Now, what else are we doing here? Well, when we're burning methane. So, right, this is when we burn 1 mole of methane, it's minus 890 kilojoules per mole. Now, 890 is smaller than 965, isn't it? So where do I put on methane? Well, I'm going to have to put on methane somewhere about here. I should put the oxygens in there, but I probably won't bother. Right, so methane there, and we know, yeah, when we burn methane, move this to the side, you get, when you burn methane, turn it to carbon dioxide and water, you get minus 890 kilojoules. Now, what are we interested in? Well, we are interested in the enthalpy change when you form methane from the carbon and the hydrogen. So we're interested in that little blue line there. Okay, now what's the value of that blue line? Well, we can see all we've got to do is we have got to subtract 890, not worrying about the sign, from 965. Okay, and that's going to give us that value there, because we did that is going to be 75. And then we think about the sign. Well, what is the sign? Well, the arrow is going down, so that tells us the sign should be negative because it's an exothermic change. Okay, so that's how you do that one, using one of these enthalpy diagrams rather than as a Hess's law cycle. So if you've got a problem like these in the exam, then I wouldn't bother doing it this way, this new way. Definitely not. I'd do it the old way. But it's just to give you an idea with, that you can do it this way, because when we're going to calculate lattice enthalpies in the next couple of videos, and it's much easier if you use this new way. When you're doing lattice enthalpies, you can do it the old way. People generally speaking don't, because it's easier to do it this way. And also you need to be able to do it this way, because in the exam they will give you an energy level diagram like this and you have to fill in the gaps. So if you don't understand what it is because you've always been doing it that way, that's going to be no good. Okay, so that's going to be in the next video.